you can guess that mobility is a parameter that defines how easier it is for a particle to move or how quickly they move. But when we talk about a semiconductor, the charge carriers, which are holes and electrons, are already moving in random directions with no net movement in any particular direction. So, mobility in a semiconductor is defined relative to electric field, because unless and until you apply electric field in a semiconductor, charge carriers will not have any net movement. So, for a semiconductor, mobility, which is represented by mu, is equal to drift velocity, which is acquired by the carriers per unit electric field which is applied across the semiconductor. Vd is drift velocity and E is electric field. Now, when we talk about drift velocity, you know that drift velocity is actually an average velocity, meaning that there might be some instances where the speed of the net movement of electrons may be greater than Vd. Similarly, we will have also some instances where the velocity of net movement of electrons is smaller than drift velocity. Assume that tau is the relaxation time. Relaxation time is defined as the time between two successive collisions. Now, we assume that, for example, say we have two atoms like this and an electron like this. First collision will take place here and second collision will take place here. The time taken by an electron to come from first point to second point is tau. We will assume that the velocity of electron just after the first collision is 0 and the component of velocity of electron in the direction of electric field just before the second collision is Vd, where Vd is the drift velocity. We also know that force is equal to mass into acceleration. Here, in our case, we have assumed acceleration in the direction of electric field and also force by an electrostatic field on a charge q is equal to QE. If we equate the two equations, then we will have mass into acceleration equal to QE, giving us acceleration to be equal to QE divided by m. You know, electron is kept in an electric field, therefore its velocity will be increasing, so Vd is actually equal to a tau. We have taken minus q because charge on an electron is negative. However, we have already considered the effect of negative sign, as we already know that since negative sign is present, the electron will move in the direction opposite to the electric field. So, we will not consider negative sign here and will only talk about the magnitude, as negative sign we have already considered initially. If it was a hole, then there will be no negative sign and the drift velocity will be in the direction of the electric field. Now, drift velocity can also be written as q into tau divided by m multiplied by e. Compare this equation with the standard equation of mobility, which was drift velocity is equal to mobility into electric field. On comparing, you will find that mobility is actually equal to q into tau divided by m. It should be clear to you that negative sign only represents the direction in which the drift velocity will be acquired. Also, we know that we have two different types of charge carriers in a semiconductor, which are holes and electrons. Mobility of a free electron is given as magnitude of charge of an electron multiplied by relaxation time of a free electron divided by effective mass for free electron for conductance calculation. This is the first formula in which you will be using the effective mass for conductance calculation. Similarly, for holes, we have mobility to be equal to Q, which is the magnitude of charge on a hole multiplied by relaxation time of holes divided by effective mass of holes for conductance calculation. You should also remember that the mobility for electron is always greater than mobility of holes for the same semiconductor. That's all for now. We will talk about mobility a little more in the next lecture.